particle is not a stellar neutrino, as postulated here, but it could be something different. Could be an axino, could be hidden gaugino, or something more ad hoc. Okay. However, currently, the dark matter origin of this TKB line is in question. So this signal, if these parameters are correct, and according to what we know about the matter distribution in our galaxy and the other objects, so first of all, you could calculate what is the predicted signal coming from the Milky Way center, and then this signal should be at the reach of the Chandra X-ray observatory. However, this line was not observed. Also, the signal in the Coma, Virgo, and Ophiuchus galaxy clusters is also predicted to be at the reach of the Suzaku X-ray observatory. However, these authors, they made a search in the Suzaku data in this class of galaxies and didn't find such a line. Also, it was done an analysis of different dwarf galaxies, actually stacked spectra of dwarf galaxies, and it was demonstrated that this signal, if it is correct, should be at the reach of XMM Newton and should be observed with a significance of 8 sigma. However, this line was not observed. So these authors, they made an analysis of 81 galaxies in the Chandra data and 29 galaxies in the XMM Newton data. Again, in this set of data, they were expecting a large significance for this X-ray line. However, the line was not observed. And then also in recent times, it was questioned, the analysis by his authors, claiming that they had taken into account all the possible atomic lines that could be originated from these objects. Okay, so it was argued that these authors forgot about the potassium and the chloride lines, that they could be much stronger than initially believed. But nevertheless, this argument has been refuted and then counter-refuted and refuted again by different authors. Okay? So at this point, it is not clear, but hopefully the future Astro-Age mission will clarify the nature of this line. The Astro-Age mission, by the way, will be launched in 2015 or 2016. So perhaps in 2 or 3 years, we know whether this line is indeed coming from an exotic origin, or it is of astrophysical origin, or some atomic line. So the second candidate I would like to discuss are the weakly interacting massive particles. This is the preferred candidate by many people. So this is basically a sketch of this mechanism. So this mechanism has 2 postulates or 2 assumptions. The first one is that the matter particles interact in pairs with standard model particles via this effective interaction. And then the second assumption is that the matter particles were in thermal equilibrium with standard model particles in the early universe. Okay? So this means that at high temperatures, the yield or the number density of the matter particles per Coulomb volume followed the equilibrium distribution. And then as the temperature drops below the matter mass, so at very high temperatures, if an equilibrium, this means that the production rate is identical to the annihilation rate. However, when the temperature drops below the matter mass, the matter particles can annihilate into standard model particles. However, they cannot be regenerated simply because the kinetic energy of the standard model particles is not large enough to produce the matter particles. Okay, so below a temperature equal to a matter mass, the number density of the matter particles starts to decrease. This process of destruction of the matter particles continues in a static universe. It will continue until there is no matter particle remaining in our universe, but our universe is expanding. And there is a moment in the history of the universe where 2 matter particles are too far apart to annihilate with each other. So this corresponds to a temperature which is 1/20th or 1/30th of the matter mass. And after this point, the matter particles have a constant number density per Coulomb volume. So when this happens, depends on what is the annihilation cross-section of the matter particles in the standard model particles. And it can be calculated using standard techniques that the relic abundance of the matter particles is 3 times 10 to the minus 27 divided by the annihilation cross-section multiplied by the relative velocity and then thermally averaged. So from this expression, one finds that to reproduce the correct relic abundance, omega h squared equal to 0.1, then the cross-section multiplied by the velocity must be equal or close to 3 times 10 to the minus 26 centimeter cube per second. So it is quite illuminating to play here with the numbers and to cast these numbers 3 times 10 to the minus 26 as 1 picobarn times the speed of light. So at the time of freeze-out, the matter particles were quite relativistic. So this expression tells us that if this interaction has a cross-section of the other 1 picobarn, So this means that if this is a weak interaction, then one can reproduce quite naturally the observed dark matter abundance. That is the reason why these candidates are called weakly interacting massive particles. Okay. So again, one can continue playing with the numbers and doing some numerology. So one can expand this effective interaction to have here some mediator in the T channel. So in this case, the cross-section goes with the coupling constant, the matter particle with some other particles to the fourth power, and then divided by the mass of the matter particle to the second power. So now the requirement of this cross-section is of the order of 1 picobar, and if we assume that this cross-section, that this coupling constant is of the order of 0.1, is of the order of weak coupling constant, then one has a prediction for the matter mass that is between 100 GeV and 1 TeV. So here we have a nice and consistent picture where we have dark matter particles with mass in this range, with a cross-section, with a coupling constant, which is of order 0.1, which is a quite reasonable coupling constant. And then if this particle is stable and was in thermal equilibrium with standard model particles in the universe, then the abundance of this particle today is predicted to be equal to 0.1, which is exactly what we measure for the dark matter particle. So this mass range is also quite interesting because now there are many experiments that are exploring this energy range. So it's just a few of them. So here, Lux and Xenon, they are probing this effective interaction in this direction, so the scattering of the matter particles with some model particles. I will not discuss this detection strategy in my talk because it was covered before by José. Then the second detection strategy consists in looking at this diagram in this direction. So it is the production of the matter particles from collisions of standard model particles, which is precisely what is being done by the CMS and Atlas experiments at the LHC. And finally, one looks at the diagram in this direction. So one has the annihilation of the matter particles to produce standard model particles. And this is the social strategy that is being followed by these experiments. So these experiments, by the way, they were not designed to detect the matter particles. They were designed for high-energy astrophysics, so MAGIC, Fermi, Veritas, and HESS, they are gamma-ray telescopes. So they were designed to understand active radioactive nuclei, gamma-ray bursts, etc. But since they are there anyway, we can try to use these instruments to detect the annihilation products of the matter particles. Pamela and EMS, they are searching for cosmic antimatter, again, thinking in astrophysical processes, thinking in trying to explore or understand the mechanisms of propagation of charged particles in the galaxy. But again, they are exploring this energy range of several GeV to a few TeV. So again, why not using these instruments to detect the postulated annihilation products of the matter particles? And then IceCube, which is a neutrino telescope that, again, could be useful to constrain or perhaps even to detect the neutrinos that could be produced in dark matter annihilations. So the general strategy for indirect matter searches is as follows. So here one has two matter particles that annihilate producing electrons, positrons, neutrinos, antiprotons, gamma rays. So the production is described by one function called the source function, which is the number of particles produced at a given position in the galaxy per unit volume, per unit time, and unit energy. So you have this expression, so it is proportional to the density of the matter particles squared, so to the number density, so it is the mass density divided by the matter mass, and it is squared because we need two dark matter particles to have one annihilation. Okay. So it's also, of course, dependent on the annihilation cross-section. The larger the annihilation cross-section, the most probable it is processed, and of course, the larger the flux is. And then finally here, dN over dE is the energy spectrum of particles produced in this annihilation. So now these particles have been produced somewhere in the galaxy. They have to propagate to the Earth. So in the case of gamma rays and neutrinos, they propagate in a straight line. So here the propagation is quite simple. In the case of the charged cosmic rays, namely electrons, positrons, antiprotons, antideuterons, etc., this propagation is more complicated because charged particles, they are influenced by the tangled magnetic field of the galaxy. So at the end, this is described by the diffusion process, which is pretty much understood, although there are some uncertainties. Okay. So propagation is more or less under control. So at the moment, the largest uncertainties, they come from the source function. First of all, they come from the determination of the dark matter density distribution, which is quite unknown. So at the moment, it relies on dark matter simulations, on embodied simulations. And you can see that these embodied simulations, they produce different results, especially when you go close to the galactic center. So when you are far from the galactic center, in particular, the Earth is here, 8.5 kiloparsec from the galactic center. All these dark matter models practically converge. But as you go to the center of the Milky Way, which is where the annihilations typically take place, then there are less discrepancies between different halo models. Secondly, there are also uncertainties coming from particle physics models. So here we have the matter mass that is typically fixed, by some analysis. The energy spectrum of the matter particles, the energy spectrum of particles is postulated. One assumes a given annihilation channel. And then here, one of the large uncertainties is what is the expected annihilation cross-section of dark matter particles to produce standard model particles. So this we don't know, but the well-motivated choice is to assume that this annihilation cross-section is equal to 3 times 10 to the minus 26, which was the number that was required to produce thermally dark matter particles in the universe. So this is the canonical annihilation cross-section for WIMP dark matter, and it's the first milestone for experimental searches. So most experimental searches, they aim to get to this number, because it is below this number where it is most likely to find the signal of dark matter annihilations. So now let me discuss some of the results in different messengers. So first of all, positrons. So this is the measurement of the positron fraction by the AMS collaboration last year, extending up to 300 GeV. And this is in stark contrast with expectations from spalations of cosmic rays in the interstellar medium that predict that this positron fraction should typically decrease, at least for the simplest propagation models. However, here, the behavior that was observed was completely different. It was observed a rise in the positron fraction that was interpreted by many authors as coming from dark matter annihilations or decays. Okay, I'm not going to discuss about that anymore because that is quite old already. So this is the release of data by AMS last year. So this year there was a new release of data. So this corresponds to this extra data point at 500 GeV. And here it was pointed out by the AMS collaboration the existence of this change of the trend that was interpreted by the collaboration as a hint for dark matter annihilations, although many people question this conclusion. Okay? So in any case, with this data, what one can do is to set limits on the dark matter properties by making a careful assumptions or some well-motivated assumptions about the background. And these are the corresponding limits on the annihilation cross-section as a function of the matter mass for annihilations to electrons, positrons, mu plus, mu minus, tau tau, P bar, and WW. And what is interesting about this plot is that for some channels, in particular for E plus, E minus, and for P plus, E minus, we are now crossing this milestone of 3 times 10 to the minus 26. So this is one of the opportunities where dark matter could have shown up. Nevertheless, dark matter WIMPs did not show up in this data. The second interesting channel are antiprotons. So these are the measurement of the antiproton flux and the antiproton to proton fraction by the Pamela collaboration from 2010. These are still the latest data which are available. And here, all these dotted lines and all these dashed lines correspond to different models, astrophysical models, of production of antiprotons via proton-proton collisions. Here, one proton is a high-energy cosmic ray, and here the second proton is some halogen atom, halogen nucleus in the interstellar medium. So these are the corresponding predictions for theory. These are the corresponding data points, and here you can see a fairly good agreement between the prediction from theory and the observed antiproton to proton fraction. So this means that here there is little room for the exotic component of antiprotons, and this allows to set quite stringent limits on the annihilation cross-section coming from the antiproton channel. These are the corresponding limits. So here for annihilation into B bar or tau tau, WW, gamma gamma, etc. This comes from higher order processes from electroweak bremsstrahlung. And here what you can see is that at the moment antiprotons are not yet sensitive, at least for the mean values of the parameters of the propagation parameters. It is not yet sensitive to the thermal cross-section. Okay? So here it's also important to mention, in the case of antiprotons, there are large uncertainties coming from astrophysics, in particular from the choice of the halo model, and even more importantly from the choice of the propagation model, to the extent that the limits range or vary or more than one order of magnitude, depending in particular of which propagation model you choose for the antiprotons. Okay. So these are the present limits. Now AMS promises that after 10 years, they will have this very, very accurate measurement of the antiproton-to-proton fraction. This will allow to set much more stringent limits on the dark matter properties. And in particular, with AMS data, after 1 year, after 3 years, it will be possible to cross this barrier of 3 times 10 to the minus 26. So again, here in a few years, we'll have a chance to see dark matter particles in the AMS data as an excess in the antiproton-to-proton fraction. Also, one can do searches of antinuclei, in particular antiuterons. So antiuterons form when one antiproton and one antineutron coalesce, they merge together. So cosmic antiuterons have not been yet observed. This is the expectations coming from spalations of cosmic rays on interstellar medium. And this is the present limit coming from the best collaboration. And you can see that expectations from theory, from astrophysical processes, is 4 orders of magnitude away from the present sensitivity. So it's not surprising that no antiuteron has been observed at the moment. Okay? So now AMS will increase the sensitivity to antiuterons by 2 orders of magnitude, and gaps by also by a little bit more than 2 orders of magnitude. And this offers new opportunities to search also for dark matter annihilations. Okay? So it is clear that the antideuteron flux is highly correlated to antiproton flux, because if you have antideuterons, for sure, you must have antiprotons. So there are strong limits on the antideuteron flux coming from the non-observation of an antiproton excess in Pamela. And these curves here show the corresponding upper limits on the antideuteron flux that are derived using the upper limits from Pamela on the antiproton flux. Okay? So here, this is the maximum amount of antideuterons that you might hope to see with our present knowledge from the antiproton-proton fraction from Pamela. Okay? So you see that in the case of 100 GeV, for the matter particles annihilating to W, this is marginally at the reach of AMS2. Okay? This, I insist, these are upper limits. In the case of PV, it's a little bit better, especially for large masses, but you see that in any case, it is likely to be out of the reach of the AMS2 experiment. However, here one should mention that there are some uncertainties in the prediction coming from nuclear physics. So this prediction depends on one parameter called the coalescence momentum that is not accurately known, and it depends to the third power of this parameter. And this means that these predictions, they can change largely depending on what is the value of this coalescence momentum. Okay? But in general, I think that it is quite difficult that AMS will see cosmic antideuterons, at least according to our knowledge coming from theory. One can go a little bit beyond, not just considering antideuterons, but also considering antihelium. So the antihelium is formed when 2 antiprotons and one antineutron coalesce. So this was analyzed this year for the first time. And then here again, we see that the observation of antihelium is very far away from the sensitivity of AMS2. It is 2 orders of magnitude away from AMS2. However, the observation of antihelium could be at the reach of the GAPS experiment if this is in the form of a satellite. So GAPS is typically, in the present setup, it is a balloon experiment, but there are some plans to make a GAPS experiment send it to space, and then if it is feasible, if it is the case, then it could be possible to observe antihelium in the far future. And finally, in the last part of my talk, I will concentrate on gamma rays, which is quite a rich area. So first of all, which are the most promising targets to detect gamma rays from dark matter annihilation? So this is a map of the sky, assuming a perfect subtraction of the galactic foregrounds. So here, this is of course done with embodied simulations. And here, the brightest spots correspond to maybe to the most promising targets for dark matter annihilation. So here, clearly, the most promising target is the galactic center. This is the brightest point in this, the brightest region in this plot. However, here the search is challenged by the large astrophysical backgrounds. The second interesting target are the dwarf galaxies. These are actually quite interesting because here we are far away from the galactic center, from the galactic disk. So here the galactic foregrounds are expected to be smaller. Very important target is not just to focus on the galactic center, but extend the search to some larger latitudes and longitudes, is what is called the galactic halo. One can look at annihilations coming from extragalactic distances. It's called the extragalactic background, extragalactic diffuse background. Also, one can look at galaxy clusters. And finally, one can look not at different morphology of the signal, but looking at special features in the energy spectrum. Okay. So here we have a generic problem for discovery, which is that for typical channels and for typical masses, the expected gamma ray flux from dark matter annihilations is well below the expected backgrounds. Okay, so it's an example with expected flux from dark matter particles annihilating into PE bar with a mass of 500 GeV compared to the measurements of the gamma ray flux in the same region of the sky. This is some region in the galactic center. So here you see that the expectations from dark matter annihilations is factor of 20, 30 below the background. So this means that it is necessary, in principle, to understand the background to the 10% or to the 1% accuracy in order to detect this signal and to distinguish the signal from the background. So here the message is that it is necessary to select targets and to devise search strategies which optimize the signal to background ratio. So different studies have been done, different studies have been done, and some of the most promising targets for detection are dwarf galaxies, technically search for sharp gamma ray spectral features, and possibly the galactic center. Okay, so here, of course, it is challenged, I insist, because of the existence of large backgrounds, but at the same time here the signal is also expected to be strongest. Okay, so these are the 25 known dwarf galaxies, or the Milky Way satellites. So of course, not all of them are suitable to make searches for dark matter annihilations. For example, Sagittarius is very close to the galactic disk, so this one is excluded from the analysis. So at the end, only 15 of those dwarf galaxies is used for the search of dark matter annihilations. And this is the simulated signal of dark matter annihilation. This is what we expect to see someday in the sky. This is at the moment not observed, and this allows to set quite stringent limits on the annihilation cross-section as a function of the matter mass for different annihilation channels. Okay? So this is, as usual, this is the expected limit, and this is observed limit, so concentrate only on the solid line. So in the case of mu plus mu minus, then at 10 GeV, the limit is about 10 to minus 25, so this is well above the cross-section for a thermal relic, which is 3 times 10 to minus 26. However, it is interesting to note that observations of the Fermi-Lat of dwarf galaxies already cross this magic number of 3 times 10 to minus 26 for 2 channels, for PE bar and for tau tau. And you can see here that in the case of PE bar, present experiments can probe the thermal region for masses below 20 GeV, and in the case of tau tau, also about 20-30 GeV. Okay? So again, this is a chance where matter particles could appear in the sky, but didn't show up. So these are the strongest limits for masses, for low masses. At largest masses, the most suitable instruments is not the Fermi-Lat, because the effective area is very small for large energies. So the most suitable instruments are Cherenkov telescope, ground-based telescopes. And here you can see, for example, for mu, this is the limit by the Fermi-Lat, and this is the limit derived by the magic collaboration from observations of the CA1 dwarf galaxy. Okay? There have been some developments in the last month, actually, in the searches of dark matter particles in dwarf galaxies. So this is a plot presented by Anderson in the Fermi Symposium in Nagoya 1 month ago, with the latest result of the Fermi collaboration using the past 8 and using 6 years of Fermi data. This is the limit that I showed before by Ackermann from 2014, and this is the limit that was derived by the Fermi collaboration, now with the latest data and with the latest reconstruction algorithm for the events. Okay? And now you see that in the case of PE bar, dwarf galaxy observation can probe dark matter particles, thermally produced dark matter particles with masses below 100 GeV. The second important and interesting search strategy is to search for gamma ray spectral features, for gamma ray lines. So these are the limits derived by the Fermi collaboration in the middle of last year, in May 2013. So these are the 95% confidence limits ordination cross-section to gamma gamma as a function of the matter mass. See, it is between 2 GeV and 300 GeV. And then here there was no significant excess, and this means that there is no indication for a gamma ray line in this range. Okay. So it is quite interesting that here you see that the limits on the cross-section, for example, at 100 GeV, is about 6 times, 7 times 10 to the minus 27. This is well below this canonical value of the cross-section 3 times 10 to the minus 26. So of course, this is very exciting. However, one should remember that gamma rays are not originated, gamma ray lines are not originated at tree level because the matter particles do not interact at tree level with photons. The matter particles, according to the WIMP paradigm, interact with some other particles, and therefore the gamma ray lines appear only at the one loop level. So this means that the expected cross-section from theory for WIMP dark matter for the cross-section to gamma gamma is equal to ephemeral cross-section and then multiplied by a factor of alpha squared coming from this loop factor and because of these 2 extra coupling constants. So expectation from theory for this cross-section to gamma gamma is not 3 times 10 to the minus 26, but it is about 10 to the minus 30. So you see that even though it is quite an impressive achievement that they could constrain gamma ray lines to these very, very precise numbers, this is still far away from the expected cross-section from theory. The search for gamma ray lines have been extended to higher energies by different Cherenkov telescopes, in particular by the HESS collaboration, and these are at present the best limits on gamma ray lines at largest masses. So again, this is below 3 times 10 to the minus 26, but as I said before, the expected cross-section is about 10 to the minus 30. So at least with gamma ray lines, it is still quite far away from the situation of the detecting signal. And these are the limits that were presented by Albert in the Fermi Symposium 1 month ago. And yeah, the increase in the limits is a factor of order 1, which is not too significant, at least for dark matter searches. Okay, so in the next 10 minutes, I would like to discuss the situation in the galactic center. So this is the typical signal map from dark matter annihilation. So this is a galactic latitude. This is, sorry, galactic latitude, galactic longitude. And then from dark matter annihilations, one expects a signal which is relatively, which is quite spherically asymmetric and which is relatively faint. So typically, a factor of 10, a factor of 50, smaller than the backgrounds that are dominating the emission in the whole sky. Okay? So it was done an interesting analysis by different authors in the last few years, in particular early this year by Thailand and collaborators. So this is the measured gamma ray flux by the Fermi collaboration at different energies, different energy beams between 0.3 and 1 GeV, 1 GeV, 3 GeV, 3 GeV, 10 GeV in the region with galactic latitude smaller than 5 degrees and galactic longitude smaller than 5 degrees. Okay, so it's the measured emission. And if one wants to extract from here the matter signal, one has to subtract, first of all, the sources from the Fermi catalog. So, for example, these ones are sources. One has to subtract the spatial template for the diffuse galactic emission that has different components, has a pi0 component, Bremsstrahlung, and inverse Compton scattering. So this is the template that these authors used. One also has to extract the emission coming from the Fermi bubbles, which is by now established. And also one has to extract the isotropic extragalactic component. Okay? And they did this, and this is what they obtained. So of course, these are all the expected contributions to the gamma ray flux. So they expected in principle that this residual would be completely blank, but nevertheless, what they found is here some significant excess in the galactic center region. Okay. So it was quite exciting because, okay, it has a, you see that it's roughly spherically asymmetric, so this is perhaps compatible with the matter signal. So it's the corresponding spectrum that they reconstructed for this residual, for something which is not accounted by all these different components of the total gamma ray flux. And this is a spectrum that they obtained. These are the corresponding data points. And then this curve here is the best fit, assuming dark matter annihilations into V bar with a mass of 35 GeV and with a cross-section 10 to the minus 26. Okay? So actually the significance of this fit is about 40 sigma. So of course, this doesn't make any sense to talk about these very large sigmas. But however, what is clear is that there is a significant excess in the galactic center. and that this excess can be well fitted by Raman annihilations with parameters which are pretty close to the ones which are expected for a thermal relic. Okay. So this is in the innermost part of the galactic center. So this part is complicated because it could be populated by sources. So they did in the same paper a second analysis, removing the band of galactic latitudes smaller than 1 degree. And even if one does this, one observes here an excess in the galactic center. These are the residuals in different energy beams, a residual that extends up to very high latitudes, up to 10 degrees. And it's the corresponding spectrum that was reconstructed for this residual, the energy spectrum, now in this region. And it is pretty much consistent with the spectrum that was observed in the innermost part of the galaxy. You see, with the same mass, similar mass, and with a similar cross-section. Okay. So this analysis assumes a very concrete spatial template for the galactic diffuse model, which is this one. So of course, one may wonder whether the existence of this excess is simply due to the choice of the wrong template for the galactic foreground. So it was analyzed by Calore, Hollis, and Veniger. So they considered 60 different models of galactic diffuse emission. And in all these 60 different models that take into account very extreme ranges for the parameters of propagation and injection of electrons from supernova remnants and so on, in all these 60 models, they found an excess in all of them, and they found an excess with a spectrum which is pretty much the same in all these galactic models. Okay? So this is the galactic excess. So this is the galactic excess derived by these authors with only the statistical uncertainties. And in here, you can see the galactic excess also including the systematic uncertainties from the modeling of the diffuse background. Okay. So here's the corresponding fits. So Raman annihilations into B bar fits well the data. So of course, maybe I should mention that compared to the analysis by Dalla et al. That has here a sharp cutoff at about 10 GeV, the analysis by Calore et al. Observes this tail extended to high energies. But anyways, the annihilation to B bar fits quite well the data. The p-value is 0.43. So of course, here the errors are correlated. The systematic errors are highly correlated. So here, don't be misled by this sharp drop-off. And they also consider the fit corresponding to the broken power law, which is what one would expect perhaps from some astrophysical source. It is this line here. And in this case, the p-value is not, well, it is slightly better than in the case for annihilation to B bar, but not significantly better. Okay? Other channels can also fit excess. For example, annihilations into charm, anti-charm. Here the p-value is 0.44, so it is quite similar to annihilations into B bar. And annihilation into tau-tau also can explain this excess, but with a smaller p-value. So this is now quite interesting because this criticism that we did, that we only consider one template model, does not apply. This excess exists no matter which template model you use. So now it is the moment to make more harder tests to the Raman interpretation of the galactic excess. So in particular, if this excess is indeed due to dark matter annihilations, one expects the signal to be roughly spherically symmetric. So in particular, it should be north-south symmetric. So this is the emission in this region 1, which is in the north hemisphere, region 2 in the south hemisphere. And you see that the spectrum is quite similar and with the same intensity in these two regions. So this means that the signal is indeed north-south symmetric. Also, the signal should be east-west symmetric. So this region 6 and 8, region 7 and 8. And indeed, the signal seems to be east-west symmetric. So it is roughly spherically symmetric, and in all the cases, in all these regions, with a similar spectrum. And also one expects that the signal should be stronger in the galactic center and weaker as you go away from the galactic center, and this is indeed what one observes. So in the galactic center, it is quite strong, and then as you go away from the galactic center, region 9 and 10, the signal becomes weaker and weaker. So this is, by the way, 10 to the minus 5, this is 10 to the minus 6. And all this is consistent with the contracted NFW profile. So also one can make the best fit points, assuming annihilations into B bar in all these different regions. And it's quite remarkable that in all these regions, they are all compatible with all these different p-values. They are all compatible with Raman annihilations, into B bar with a cross-section which is 1.7 times 10 to the minus 26, and the mass which is between 40 and 50 GeV. So there have been different tests to the Raman interpretation of the galactic center excess. First of all, that the required mass and cross-section could be large enough to produce an observable signal from dwarf galaxies. So these are the published limits by the Fermi collaboration. This is the observed limit, and this is the expected values of the cross-section assuming this interpretation of the galactic center excess. So this region is still allowed by the present searches. However, there was this new developments in the Fermi Symposium last month. These are the corresponding best fit regions derived by different authors, and this is the corresponding limit that was derived by the Fermi collaboration using the past 8 and using the 6 years of Fermi data. So you see that there is some tension. It is not totally ruled out, but there is some tension between the dramatic interpretation of the galactic center excess with observations of dwarf galaxies. In the next year, there is some confidence that we could really probe this region of the planetary space with dwarf galaxies. So this is the expectation for the Fermi satellite using past 8 and with 10 years of observation. This is the corresponding limit, and then you see that it will be possible to firmly rule out or to firmly confirm the existence of an excess in this region of the planetary space. If this signal is true, I mean, if the matter particles indeed annihilate into B bar with a cross-section which is 10 to the minus 26 and with a mass of 40 GeV into B bar, the big quarks produce antiprotons, so this could also produce an antiproton excess, and this is the limits on the antiprotons coming from the Pamela experiment for different propagation models, and this is the best fit region coming from the galactic center excess. So here you see that there is some tension between the antiproton measurements and the dramatic interpretation of the galactic center excess. Also, there is some tension between this interpretation and observations of radio coming from the direction of the galactic center. And also, this interpretation could be tested in direct detection experiments. Also, this is quite model dependent. So these are different models of the matter annihilations that produce the required cross-section into B bar, and this is the corresponding cross-section, spin-dependent cross-section, and this is the sensitivity of future experiments. So you see that for some of these models, which are actually models where the matter particles interact with big quarks via T-channel interaction, so these ones, this class of models, will be at the reach of the LAX experiment and eventually at the xenon-quantum experiment. So the message is that if this signal is correct, then LAX and xenon-quantum might see a signal. Okay? That's how some models that could escape detection forever. And finally, there are some astrophysical backgrounds that are not very well understood and that were not included in the templates. For example, millisecond pulsars that have been argued to be able to explain the galactic center excess with the same spectrum and with a recurring intensity. And also, all these diffuse models, they assume that the galactic center was quite in a steady state. However, this is a very strong assumption. So if there was an active past negative center, for example, coming from a burst event, injecting protons or injecting electrons, then one could produce an excess which is, it was argued to be consistent with the observed galactic center excess, although here the morphology is, one has to say, it is quite different to the one that one sees with the Fermi data. All in all, I would say that the matter origin of the galactic center excess is still unclear. Although it is something to keep an eye on. So these are maybe just, I need 3 more minutes perhaps. These are maybe some of the main plots that I have shown here today. There are currently strong limits on the annihilation cross-section. So for different channels, one has crossed this magic number of 3 times 10 to the minus 26, using positron data, in particular for E plus in minus final state. And in the case of our galaxies, for PE bar, currently, it's not yet published, but it is advertised, so to say, for masses below 100 GeV. So now you see that we have been crossing, or it has been possible to cross these magic numbers. So now the question is whether the wind paradigm is not challenged by indirect searches. Okay, here was expected to find a signal, but no signal was expected. And I would say it is not challenged, at least for an interesting class of models. Okay. So to find or to identify this class of models, this is perhaps the most theoretical part of my talk. One decomposes direction cross-section in low velocities, so these parameters A and B are calculable, and here this velocity depends on the astrophysical conditions. Okay? So the demo freeze out, the velocity was large because the matter particles have large kinetic energy, and one can calculate that the average velocity squared of the matter particles demo freeze out was about 0.3. On the other hand, today at the galactic center, the typical velocity of matter particles is about 10 to the minus 3 in units of the speed of light. So then one could consider here two different scenarios. So if this parameter A is much bigger than B, V squared, so if the velocity-independent part is much bigger than the velocity-dependent part, then the cross sections at the time of freeze out and at the time of today in the galactic center are very close to 1. On the other hand, if for some reason the velocity-independent part is very small, much smaller than the velocity-dependent part, then the annihilation cross-section today in the galactic center will be much, much smaller than the annihilation cross-section at the time of freeze out. So it's the class of models that could escape detection today in indirect dark matter searches. So here it is as a mathematical exercise, but this actually happens for a class of interesting models, namely when the matter particles are marginal fermions, or they are scalar particles. So in this case, the annihilation in the galactic center takes place at very low velocity, and in this limit, there is no preferred direction, so this means that the total angular momentum in initial state is equal to 0. And then if the annihilation is into a fermion and anti-fermion, in the simplest case, the total angular momentum in the final state is equal to 1. So clearly, this process violates angular momentum. So to have a final state that preserves angular momentum, one has to introduce here a heuristic flip, which means that the rate of annihilations is suppressed by the mass of the fermion divided by the matter mass to the second power, in the case that the velocity is equal to 0, and otherwise by the velocity squared. So in here one has models, for example, annihilations into electrons, where indeed the velocity-independent part is 1 million times smaller than the velocity-dependent part, and similar for muons, and similarly for uptype quarks. So for this interesting class of models, namely the matter particles, which are Majorana or scalars, that annihilate into light fermions, the expected annihilation cross-section today is of the order of 10 to the minus 31. So it is not surprising that no signal has been observed. So with this very small number, one may think that it is impossible to test this class of models. However, given that the cross-section is so small, the higher order effects could become important. So here by higher order effects, I mean, for example, the emission, associated emission of a gauge boson. So in this case, one can construct a final state that has 0 angular momentum involving this gauge boson, and there is no suppression by the mass insertion. So this process is, however, suppressed by the extra coupling constant and by the three-body phase space, but some order of magnitude estimates show us that the expected transition cross-section today for this 2 to 3 process is of the order of 10 to the minus 28. Okay, so in this class of scenarios, namely Majorana fermions or scalar dark matter particles, the target for detection is not 3 times 10 to the minus 26, but it is 10 to the minus 28. So this class of models also have the peculiarity that they predict a very sharp spectral feature, very close to the endpoint of the spectrum, and this allows to search quite efficiently for these scenarios, and these are the corresponding limits for the matter particles annihilating to mu plus, mu minus, and the photon. So you see that for 200 GeV, the limits are only a factor of 1 order of magnitude far away from the expected value for a thermal relic. And in the case of P bar, it is 8 bit worse. Okay. So these are my conclusions. Thanks, Enrico. So I think maybe the most interesting conclusion is that we have entered an era in dark matter searches, called an era, where many experiments are operating with the necessary sensitivity to observe a dark matter signal. So in the case of indirect searches, we have crossed this magic number of 3 times 10 to the minus 26. So in the last years, in particular in the last year, several anomalies have been reported in cosmic ray or gamma ray observations, which may be due to dark matter annihilations or decays. However, the exotic interpretation of these anomalies is at the moment inconclusive and sometimes even controversial. Okay? And my last conclusion is, even though now we have a real opportunity to observe a dark matter signal, if we don't observe a dark matter signal in this round of experiment, it is not a moment yet to give up the WIMP paradigm, because there are some well-motivated scenarios that predict a signal which is below the sensitivity of present experiments. So the quest should go on. Thank you for your attention.
Thank you, Alejandro. Very nice talk. And a few minutes for questions or comments. Yeah.
Yes, you mentioned in the galactic center signal that an astrophysical background could be the pulsars. And also for the positrons, there is an astrophysical background. Are these scenarios of pulsar the same? So if you try to explain the positrons, you also explain the galactic center, or are they different?
They are not the same because the excess appears at very different energies. So here you see that the peak of the excess is at 2,3 GeV. So in the case of the Pamela Fermi excess and so on, they are the peak of the excess or the excess extended up to 1 TeV. So they are not the same pulsars. There is no, and also in the case of, I mean, if you want to explain Pamela and Fermi, the excess in the positron fraction with Fermat annihilations, then you require, first of all, a leptophilic channel, and this one is B bar, so this one is not leptophilic at all. And secondly, that to explain Pamela and Fermi, you require a cross-section which is 10 to minus 23 centimeter cube per second. And here the cross-section is 10 to minus 26. So it is totally different parameters. And for the pulsars, it is pretty much the same because it is, I mean, these numbers control the strength of the signal. But it cannot be the same origin.
Diego.
What is the statistical significance of the signal?
Statistical significance of the excess. It is difficult to quantify. It is difficult to quantify. In this paper, they claim 40 sigma, but it is the excess. The excess. I mean, here you see 0. This corresponds to no excess. So here there is some excess. There are, I mean, this is, I don't know, like this point, like 7 standard deviations from 0. They claim for the sigma, but of course, when you go to these very, very high sigmas, you don't expect the chi-square to be a parabola. I mean, you don't expect the errors to be Gaussian. Okay. So mean for the sigma here means that the excess is clear. The excess is clear. Now, when you take into account the systematics, I don't know exactly what is the significance of the signal because these errors are correlated, the systematic errors are correlated, but nevertheless, there is a signal. There is no doubt about the significance of the signal.
Yeah, when you were talking about the anti-deuteron annihilation, you were talking about nuclear physics uncertainties and the calculation of the cross-section. So how large are them?
How large?
How large, yes.
It is not known. It is not known how large they are. Okay, you mean for the antideuterons?
Yep.
Yeah. For the antideuterons, to simulate the antideuteron production, one uses the coalescence model, that it is a phenometrical model, so it is not based on theory. It is a phenometrical model that imposes that when two particles, proton and neutron, they are close enough in momentum space, then they coalesce, no? And this parameter P0, the coalescence momentum, must be determined with experiments. So traditionally, it has been determined using the set boson decay, and the value is about 130 MeV for this coalescence momentum. However, there are now more experiments that have measured antideuteron production. So in particular, Clio in epsilon decays has been measured by ISR in proton-proton collisions, by ALICE in particular in proton-proton collisions at different energies. And in all these experiments, the corresponding value of the coalescence momentum is different, significantly different. Okay. There seems to be a trend with the center of mass energy, that the larger the center of mass energy, the larger is the coalescence momentum, but there is no understanding of what is the or no theoretical model to calculate the coalescence momentum. So typically it is assumed that this coalescence momentum is independent of the energy, is independent of the process, but the data do not support this assumption.
Okay, thank you.
One more question, if any? No, if not, let's thank Alejandro one more time. And let us reconvene at 11:20. We shorten a bit the coffee break.
Okay, well, thank you for the invitation here, and the organization of this conference is really impressive. This is a nice place, and everything is running very smoothly. So I'd like to thank the organizers. So my goal in this talk, this is the only sort of observational cosmology talk, is to tell you, well, first a little about the Planck results, And I'm also going to talk a bit about the bicep B-mode claim and the aftermath, what Planck had to say, and also a few words about the future of the CMB, which is going to mainly be looking for B-modes and trying to get a solid detection and characterize them. So first, a little about the Planck experiment. So this is the Planck satellite. You can see the size compared to a person here that was launched in 2009. So this is a European Space Agency sort of medium-sized mission that grew a little beyond medium. And there are also a significant American involvement. So what you see here is, roughly speaking, a telescope, a little over a meter. And then this is for cooling, and there's a focal plane that we'll look at. And this surveys the sky in 9 microwave frequencies with rather broad bands. That means you're trying to collect as many photons as possible rather than get spectral information. So this is what the focal plane looks like. So these sort of remind you of brass instruments, but they're microwave feed horns, and rather than acoustic waveguides. And on the outside, you see the Italian-led low-frequency instrument, which is much like WMAP, a little more modern technology. And you can see the frequency from, well, this is several wavelengths on the outside. And then in the inside is what is really newest, which is the high-frequency instrument. So here, the only difference is the size of the horns. And this sort of probes frequencies that haven't been probed before. So what makes Planck special, not compared to ground-based experiments, but from WMAP and COBE, is the way in which the photons are detected. So this is incoherent detection. So these are basically resistive wire grids. And the entire the incoming wave almost is absorbed, and this heats up this grid. And then there's a thermistor, and this is recorded. So this is the data. And here you see that there are 2 orthogonal grids. They don't touch each other. And one picks up one polarization and the other polarization. What's good about these detectors is that they're almost at the quantum limit, which means that it's the intrinsic fluctuations of the photons that are coming in that's limiting your measurement, rather than with the coherent detectors, one is quite far away from that. And you can also go into the Wien tail of the CMB distribution. From the ground, these where the technology is more up to date, everybody pretty much uses bolometers of some type, but they have to be cooled down a lot. So just to put in perspective, we'll see some plots. This is from a while ago, so this was sort of promises from Planck, and we'll see how these have been realized. So this is the power spectrum, and this is a multipole number. So 1 over this is about the angle in radians. And here you see the temperature isotropies, anisotropies. You see the Doppler peaks, and then you see this damping tail. This has been, Boomerang detected these oscillations first in a rather rudimentary way. Then WMAP did a much better characterization. But Planck has about 10 times the sensitivity and twice the resolution of WMAP. Here, this is cosmic variance. So basically, you just have one sky. So you can't characterize the stochastic process that accurately. Then you see, the size is relative error. There's an incredible accuracy around these peaks because there are lots of multipoles. And then everything falls apart due to the, well, on the one hand, detector sensitivity, but also angular resolution. So we'll look a little at the CTT power spectrum, and I'll give you a glimpse for the 2014 power spectrum. Then the other thing that's new is from Planck, and this is something you'll only see partially realized in the next release of papers, is the polarization. So this is a log scale. This is microkelvin squared. You should maybe take the square root of this, but you can see how much more challenging this is. But you get sort of almost cosmic variance limited, and then things fall apart faster because the signal is smaller. So this is sort of, in terms of power spectrum, what Planck promised. Here you see I'll just point out some highlights. So from 30 gigahertz to 900 gigahertz, the CMB channels are in the middle. The resolution goes down with frequency because one is diffraction limited. And here it's sort of, there were problems with data rates, so it was kind of capped with a higher frequency. And here in the sensitivity, this is the LFI, and you see that it gets much more sensitive when you use this incoherent technology. So let's look at the maps. So that I wanted to put them all on one transparency, and there may be 40 million pixels that are relevant, so you can't see everything that's here, but basically the cleanest maps are in the middle frequency range, and then here you got contamination from galactic synchrotron radiation, so the galaxy gets bigger. This is the galactic plane as you go to lower frequency. So this is sort of what WMAP saw. There's slightly more sensitivity here, but then going up to higher frequency, this is new. And here you see dust in the galaxy, and then here you see more dust, and here you're in the Wien tail, so you see almost all dust. So just to sort of jump ahead when we talk about BICEP, this polarized dust map is going to be very important because this is where BICEP observed, but the dust is I think, 25 times more intense here, so this gives you a very good snapshot. Here's some more close-ups of the maps, and This is actually a diagram from WMAP, but what you should take away is that you have the synchrotron, this is Bremsstrahlung and dust. So these are sort of the enemy if you're trying to do cosmology, but by taking linear combinations of this and, well, more sophisticated methods, but that's sort of what's at heart, you can sort of clean out the pure CMB map. And this is more just, this is not so much for analyzing, but just to show you that this works. So here, by taking linear combinations, this is pretty much just all CMB, and well, we can sort of ask whether this is, you know, due to the galaxy or whatever, but it's a little like looking for grounds in coffee. It's not really that clear. I mean, it's pretty much gone. So let me switch gear and just say a few words about theory to the extent that you sort of need to know the theory behind the CMB to understand the interpretation of these maps. So the next talk will talk more about multi-field inflation and more sophisticated theoretical analysis. But the basic idea is that, well, so this is a very old diagram. Well, the inflation happens somewhere around here and creates our initial conditions. And we want to probe those initial conditions, but so the universe is opaque. Photons just scatter very rapidly and diffuse and don't go anywhere, and thermal equilibrium is established. Then there's recombination. The temperature is sufficiently low so that you don't have a plasma, but it turns into atomic hydrogen and helium, basically, which is transparent to the wavelengths in question. And then the CMB photons come to us, well, almost without scattering. So that statement is 90% true. So this is sort of a space-time diagram. Well, there's inflation changes this, but you basically have a sphere that's as large as our present horizon. In this slice, you just see 2 points, and we look back and we see what are the non-uniformities on this surface. So that's sort of the one-liner of the CMB. So this is the next 2 slides are sort of explaining inflation in a very simplified way, so that you can sort of see how we try to probe inflation, or that's what we think we're doing. So this is sort of our credo from the mid-'80s, that everything started with a scalar field and you have vacuum energy. But then this sort of thermalizes and turns into normal radiation. And because of invariance, you don't really have to know all the details about how the vacuum energy turned into normal radiation. There's sort of length where inflation starts, some uncertainty, but the invariants protect us from our ignorance. And then this is sort of a poor man's derivation of inflation that gets the right answer to sort of O1 factors. And so we have quantum fluctuations in the inflaton field, and these are proportional to the expansion rate. Then if you just want to guess, this would sort of retard and advance the end of inflation. and then you do a little math from the equations on the last page, and you get for the scalar perturbations this formula. So this is the scalar power spectrum, or its square root. You have to do a little more work to get this proportionality factor. But basically, this is a first-order ODE with an integrating constant. And we sort of observed just a few decades of this so we can reconstruct part of the potential. So that's sort of the game. Then the sort of second part of the game is tensor perturbations, which is another name for gravity waves. So these are quantum fluctuations in an expanding universe, and any quantum field gets disordered, and the linearized graviton field too. But this tells you the height of the potential or the energy scale of inflation. Now, if you want to have a bad attitude, you could say, well, this is just a first-order differential equation, and well, you have some observations, and we get a potential. That's not quite true. But when you take these two together, if you measure the tensors on two length scales, then you get a consistency relation. So this is sort of everyone's dream that one would... well, first of all, this is a really unique prediction of inflation. And then there's this consistency relation. So testing inflation, well, this is sort of the 80s, well, the universe is very flat, there are no monopoles, et cetera. Then there are the scalar perturbations, which we've mapped out very well, in part through the CMB. And then there are the tensor perturbations that are really a unique prediction of inflation. So let me just show you, this is from all the anisotropies in a sort of simple inflationary model. And you see the temperature perturbations on top. Then you see the E-mode polarization, I'll define that, which comes from the scalars, and then the TE. And then there's also the B modes, but we don't know the height. But the B modes have the shape, and that can just come from the gravity waves for reasons that I'll explain. That's in the linear theory. Then there are also B modes from lensing. Lensing is nonlinear, so, but we also think we understand lensing. So this is a very simple prediction. And here we have two windows for looking for B modes, one at very low L, so you need the full sky. You need to look from space. And then there's another window at sort of L is 70 or so, and this is where BICEP 2 and ground-based experiments are looking. So what are B modes and E modes? So, well, we like spherical harmonics. We have a sort of free field theory, so this is a good way to analyze CMB data. But there are two modes of the polarization. There should be a Laplacian here. But basically, the idea is that if you have a scalar degree of freedom, then you can get a potential on the sky, the celestial sphere. So this is theta phi. And this is the only way we can create a traceless symmetric tensor on the celestial sphere. So these are the E modes. And this you can have from a scalar theory. But then there's another orthogonal mode that's basically this, rotated by 45 degrees. That would be sort of a pseudo-scalar potential, or it would have to come from something like a vector or tensor degree of freedom. So this you cannot create from a scalar degree of freedom. And this is sort of how things project, and linearity is crucial. So we'll go, when we talk about limits on the tensor modes, there's some from T modes, but they're very model dependent. This projection is not model dependent. There's also reionization, and here this sort of creates this magnification of, this is the B mode power spectrum at low L. So for different, I guess this is closer to the real value. This also allows you to measure tau with the E mode scalar perturbations. That's something WMAP did. And here's sort of a calculation. The polarization is the, very roughly speaking, the quadrupole seen when the photons last scatter. And because there's this longer lever arm, you get this bump. I'll skip a little. Well, this is the lensing. So you know galaxies are lensed, but the CMB is also lensed. This lenses will rotate, so you sort of see part of the 45-degree rotation, so you get B modes. This is both your friend and your enemy, because you can do things like look at neutrino absolute neutrino masses, as I'll try to show later. Let's see, I'll jump. Okay, so the Planck results before 2014. So this is the power spectrum, and these are the Planck points. So this is from the papers that came out in March 2013. And the conclusion was, well, maybe not so glorious, that the 6-parameter model that WMAP said can fit all of the data, despite the increased sensitivity and angular resolution, continues to fit well. And the thing really to look at is the residuals. So we agonized a lot about this sort of dip at 1800 in the 2013 data. I'll show you a bit another way of analyzing that. That went away in 2014, and we understand that this was from systematic effects. The other thing that worried people is that you see at low L, there are more points below the red line than above. So there's sort of a deficit of power, and this is about 2 sigma. So it's hard to really know what to make of it. Now, what does this mean? I mean, one is basically fixing the model. Almost all the statistical weight comes in here, and this is sort of shameless extrapolation. These points don't really change the model very much. So this extrapolation kind of breaks down here. So that's we can sort of blow up and look, well, is there a pattern, et cetera? And that's basically I mean, one is sort of hoping for hints of something beyond the simplest inflationary models. Okay, so here you see the power deficit. Okay, one thing you can do is, so this is the amplitude, this is the deviations from scale invariance. So this term in the power series would be a spectral index, and then there's running of the spectral index. So Planck 2013 found that well, this parameter you obviously need, but this you definitely need. So there was a very high significance that scale and variance is not exact, but this parameter wasn't needed. Although we'll go back to that with the accommodating the bicep data. These are some reconstructions. This is from the power spectrum. So this is a penalized likelihood. We found a 3.1 sigma effect after the look elsewhere effect is taken into account. This is again the systematic from the Cooler line. So this result went away. These are the individual frequency channels, and when you go to very high resolution, because of the diffraction limit, you're basically going out on a limb, and you can't use these lower frequencies as a cross-check. So this is sort of a caveat about over-interpreting data. One thing that's very different from WMAP, because of the higher angular resolution, is you start getting all sorts of corrections from clusters of galaxies, and Yaev-Saldovich effect, infrared galaxies, and these have to be modeled out, and these are the residuals. So I don't want to go into the details, but this is sort of doing this correctly is crucial to having correct results and correct error bars, which is important. You can also look at the overall chi-squared. Well, this looks good, but here you're diluting things in the noise, perhaps. I don't have time to go through all of the constraints, but there are lots of, we got very nice constraints on isocurvature modes, basically no evidence for isocurvature. Then you can probe things like the sum of the neutrino masses, the number of neutrinos, and this sort of went down from WMAP, seemed to find more neutrinos. And there are a lot of things like this. Now, the big disappointment, one of the reasons to do Planck was to have a full sky map of the CMB to look at things like non-Gaussianity. And theorists were very excited about non-Gaussianity because there was this paper with a 2.8 sigma detection. Not everybody agreed with this, but there was some spread in the different interpretations, but this is a very large amount of non-Gaussianity, and there were lots of theory papers before Planck came out. And Planck really disappointed. So this is sort of around 80, 100. And here here's the measurement by Planck. So this is 2.7 plus or minus 5.8. So basically, the previous detection was a false alarm. For this local non-Gaussianity, when most of the signal comes from the quadrupole or the first few moments modulating the small scale power. And all the cosmic variance comes from the small scale. So since you have more angular resolution, you can get much better limits. So this is why Planck did a lot better. The other thing, that Planck did is there were these anomalies reported in the WMAP papers. So this is sort of if you smooth the sky with a rather large angle, so this is the degrees, and ask, well, is there more power on one side than the other side of the sky? You tend to get detections that are, maybe 3 sigma or so. And people worried, well, this could be dust, et cetera. But Planck basically found the same thing. The other thing, sort of surprise, which is hard for theory, is that this dipole modulation does not extend to power at smaller scales. That's what you would naively expect. And that's where the statistical power is much larger. So you need to come up with rather exotic models to try to explain why on these large scales there's this modulation, but not on larger scales. So that's sort of more theory issue. Another thing that was really qualitatively new, is the discovery, well, it's not quite the first work on this, but it's, there were some cross-correlation studies, but the first real precise measurement of the lensing power spectrum of the microwave background. This is about 20 sigma, and here you can see the agreement. So we'll see that in the future, one of the targets is by looking at these spectra that you can try to measure absolute neutrino masses. This is another thing beyond the power spectrum that you can do with Planck. This is the most shown plot from the Planck papers. I don't like it too much because it simplifies things a bit too much, but here's the spectral index on one axis. Here's scale invariance. And here's the scalar to tensor ratio. And phi to the 4 is not even on this plot. So there are models, there are many models that have been ruled out. Models where you sort of have some concave downward or preferred, but I mean, this is 2 sigma, so, and this vertical is much less reliable than this transverse constraint. So I think among theorists, there's been a tendency to really overinterpret this. Okay, this is a preview of Planck 2014. So these are some plots that'll be, this is preliminary, that will be shown at the conference in Ferrara, Italy next week. And here you see, sort of like in 2013, the temperature power spectrum. And the thing to really look at is the residuals. And, you sort of want to look, is there a pattern that's significant? The 1800 bump went away. This looks a bit different. I'm not, the Planck papers are coming out on the 22nd of December. Now, there are a number of things that have changed. The analysis is a lot better. We've found other corrections. Then more of the sky is used, less sky is masked, and there's, of course, more data. So it's about twice as much data. So the error bars are significantly better than 1 over the square root of 2. The other thing that is going to be presented, but with a, yes?
So you very clearly did not show what happens at L less than 50.
I'm just going to show some things. The take on all of these things is still being debated. The message I want people to take away is, the the polarization basically fits, but these error bars are not, are not to be believed at this point. There will be another 2015 polarization analysis. Here is, this starts at L is equal to 30. The polarization on lower L is extremely interesting, but it's in not as good shape. I mean, if it were, we would be presenting B-mode constraints from here. But you can see that if you don't take away the residuals, this looks pretty good. The model is being basically fits, but we really want to understand the error bars and not exaggerate where things are in the analysis. So Planck is not told, well, I mean, we don't have a choice when we release our data. This is told to us by ESA, so it might be a little different from other experiments. Okay, let me shift a little to primordial gravitational waves. This is a large value, and I just want to give a few words of caution. So what's in the Planck papers is the constraint is basically, this is a temperature template from the tensor modes, and basically beyond L is equal to 70, it just dives down, and you add this to the scalar spectrum, and you really have to trust this extrapolation. So it's very model dependent. People said that BICEP 2, I mean, theoretically it was implausible because Planck set the limit at 0.11. They didn't read the papers carefully enough, because if you allow running of the tilt, then that limit increases by a factor of 2. So that sort of highlights the model dependence of the claim. Let's see. Okay, so BICEP is like most ground-based experiments. It's based on seasons, and here you have 49 detectors, 512, then the Keck array, which is being analyzed now by the BICEP 2 team, has many more detectors. So basically the sort of message is that, well, if things aren't clear now, the data is going to get much better. Now, we talked to people working on the ground. This is before all this excitement. To someone working from space, there weren't enough frequencies, but the idea was, well, first debug your instrument, get a detection, and then add channels, but don't endlessly worry about foregrounds. So this is the plot from the paper, and you see, well, this is what you expect from lensing. These are the points that BICEP claimed was a detection, and this was just at one frequency. And you can see the tremendous improvement over BICEP 1 and all of the competition, which I think is catching up. But this was really an amazing experimental feat. The problem, this plot is for temperature. The polarization is much lower, so it's all about getting rid of foregrounds. BICEP just observed in one frequency, and their argument for having a big press conference was, well, this is sort of a hole in the clouds based on extrapolations. They didn't think dust would contribute significantly. I'm going to go a little faster so I get through everything on time, but we can go through these plots. They tried some cross correlations, but that didn't really, I mean, it just showed consistency, but it couldn't show that it was the right spectral index. This is where the Planck plot with running, and this is where bicep 2 came out on this plot. So there's really no contradiction with the Planck 2013. And then here's some models. You don't really have to change the spectrum that much. It's maybe not that nice. It goes the opposite way of the power excess, but so there were tons of papers on this. So this is sort of with the media hype. Well, this is Andre Linde, who is not known that much for modesty, and he's celebrating in this YouTube clip the discovery of B modes. So we can ask, well, was this the right moment to celebrate? And the bicep team put out in their paper, and this is not very well explained at all, these sort of models, and what the argument was, well, it's a long way from here to here, so it can't be dust, the signal is so large. But there weren't any polarized, publicly available polarized measurements in that field. Now, what happened in, this was released in September. So as I told you, well, Planck does not have the sensitivity in this field to detect B modes. If Planck detects B modes next year, it'll be over the full sky at very low L. I mean, we'll see. I think it's a bit of a long shot. But the 353 gigahertz, which is a dust-dominated channel, has polarization in the bicep field, and then you can extrapolate using the spectral index from the rest of the sky into the bicep field, and basically the message is that, well, you know, even if you have R is equal to 0.2, dust can completely explain the signal. Now, this doesn't mean that it's all dust. It's very hard to, without doing a cross-correlation, to rule out admixture of primordial B modes. And there's a project in progress between Planck and bicep 2, actually using Keck data as well, to try to see what conclusions one can get from that. Here's dust alignment is very complicated and still not understood. This is the most popular theory, where grains have really weird shapes, and they get a coherent rotation from being illuminated anisotropically. But we don't know what polarized dust looks like, and the sort of message is for the future that you really need to get very good maps at many frequencies to really be sure that you can remove the dust signal completely. Okay, so whatever the value of the tensor to scalar ratio is, well, we would like to do the best measurement possible. And this is a satellite that was proposed in Europe in 2010. A proposal for Core Plus is going to be put in mid-January. And the idea is to massively increase the number of detectors, because as I explained to you, one is limited by photon shot noise. So one can't just have better detectors. So this is 6,000 detectors plus. Let's see. I mean, here you can see this is the sensitivity. One wants to go below the lensing, and sub 10 to the minus 3 is what is claimed to be possible from space. There's competition from the ground. There are a lot of experiments underway. The Americans want to deploy 200,000 detectors from the ground to study gravitational lensing and search for B modes. So it's sort of unclear how this whole story will end. If R is rather high, it'll be discovered or confirmed in the next few years. If it's very low, well, we might go to one of these space-based experiments and just find an upper limit. Let's see. Well, the theoretical predictions are unfortunately not, it's easy to make models that predict very low values of R. There's other science with lensing. So this is the improvement over Planck with the next generation satellite. B modes is much better than temperature lensing because the B modes just shouldn't be there. This is distinguishing the normal from the inverted hierarchy. So this is just some, there are other proposals. There are 2 American proposals. This is a Japanese proposal called Lightbird. So this is less expensive. The idea is to do it faster. Since I'm running out of time, I think I'll conclude. So basically with Planck, the 2014 papers will come out on the basically last possible day this year. There will be partial results on TE and EE polarization, but we're not, the nuances are being discussed, but we're not going to say that we understand everything. There are these 2 conferences that, week-long conferences that were planned, and if you want to find out more than the sneak preview I gave you, you can look at those papers before the slides before the 22nd of December release. One thing I want to say this is a message to you that there are a lot of products that are going to be made available. So for people here who, for example, want to study statistical anisotropy and other models, there's going to be a lot of data products made available, and with rather modest computing power, it's possible to do supplementary or alternative analyses. There will be another sequence of 2015 papers basically trying to do the polarization right. The polarization at Lowell is very interesting. And turning to the sort of non-Planckian part of CMB research, the primordial B modes and lensing is sort of the new hot topic. This is sort of the remaining thing to be done in the primordial CMB. And while we have a lot of ground and balloon-based experiments are already underway, and probably there will be some space mission, maybe with people from different countries working together. I also want to make an advertisement. I just wrote a review article that'll, I guess, before this date, I put on the Astro PH and published in International Journal of Modern Physics. I also talk in there a lot about polarized dust and some of the newer issues that are going to plague CMB research that haven't been so much reviewed in your standard reviews. So I hope this gives you a little of a flavor of where CMB observation stands today and what kinds of things you can expect in the future. So thank you.
So we have time for questions.
I don't know if you're the right person to answer this. Maybe I should ask somebody from BICEP, but do you know if BICEP subtracted any preliminary dust data from Planck? Or did they completely ignore any data that was there for the dust?
I can answer that question. It's pretty well known. So the BICEP asked the Planck collaboration to have the high-frequency dust maps to use as their analysis, and Planck said no, basically because we were trying to make our own discovery of B modes. So they really, I mean, I don't want to get into the details, but there were some things taken off of a slide, but in a sort of effective way, they didn't have access to the data from Planck that would have been most useful or relevant to them. Then an agreement was reached where the two teams would work together and publish a paper together that would be based on the cross correlations between the BICEP 150 gigahertz map and all of the Planck maps in that region. And I can't talk about the results of that, but the idea is to come out with a short paper that will sort of settle the question in a rather definitive way, hopefully. I mean, just extrapolating is not, it doesn't settle the question. I mean, you could say it settles the question that, well, if you want to claim primordial gravitational waves in a sort of almost legalistic way, you have the burden of proof, and the burden of proof isn't there. But if you really want to understand what is in that field, the best thing is to sort of take all the information at different frequencies and put it together. I think that the 353 gigahertz dust map will probably become a little obsolete in a couple of years, that ground-based experiments on small fields will get deeper maps at higher frequencies and be able to do it themselves. But, you know, a lot of it, it's very difficult to make these measurements, especially from the ground. And the BICEP team, they really, what they did was fantastic in terms of creating the quality of map that they did at that frequency, which is much more sensitive than Planck.
Thank you.
More questions?
Well, there's a tension in the value of H naught, and this has been the subject of some polemic. The cosmological, it's not that significant. There was also some papers over the summer, was it last summer? Yeah, about alternative analyses and well, you should wait till the results come out. But I think these little differences have been maybe emphasized a little too much.
We just have time for one more question.
From your plots, it seems that the low L modes went really up in the TT power spectrum. So has tau changed? Is this true? And has tau changed?
Yes. You mean tau?
So I see that the low L anomaly in the power spectrum of temperature seems to, from your slide, seems to have moved up, so to be fine. And I want to ask if this is true, and also if this is due to a change in tau in the realization fraction, in the optical depth.
Yeah, it's a little. The slow L excess is a little less now, but. I think we really need to wait till the papers come out, because I mean the reason they haven't come out is that they're different likelihoods, and we're not sure that we've converged, so we're not really ready to make the 2014 statement. And personally, I feel it's a little unfortunate that we have these conferences coming up next week, but we'll show what we have and be honest about the caveats.
Okay, so thank you very much, and let's thank our speaker.